The Sherman tank's engine screamed at 2,300 RPM, pistons hammering against compression, as Sergeant Michael Hardesty shoved the throttle forward and felt the entire 33-ton vehicle lurch upward at a 45-degree angle. July 11, 1944, 14:17 hours, 3 kilometers south of St. Lo, Normandy, and the hedgerow in front of him stood like a fortress wall that nature had spent 400 years perfecting. The ancient earthen embankment rose 4 meters high, its base 3 meters thick, constructed from centuries of accumulated soil, stone, and root systems that had fused into something harder than concrete and more lethal than any man-made fortification the Germans could have designed. The tank's nose climbed the earthen barrier, 500 horsepower Continental radial engine roaring with mechanical fury, tracks clawing for purchase against roots thick as a man's thigh. And for exactly 3 seconds, Hardesty thought they might actually make it over the top. Then physics and geometry conspired against him. The Sherman's 17-foot hull reached its maximum climb angle of 48 degrees. The drive sprockets lost contact with the ground, and 33 tons of American steel hung suspended in the air with its belly armor, a mere 38 millimeters of rolled, homogeneous steel plate, exposed to whatever German anti-tank weapon was waiting on the other side. Hardesty had exactly 1 second to register what was happening before he saw the Panzerfaust smoke trail, a gray-white streak that emerged from concealment in the hedgerow 40 meters ahead and connected with his tank's underside. In the fraction of a moment it took him to scream, "Bail out!" The shaped charge warhead, designed specifically to defeat armor at close range, punched through the thin belly plate with 700 millimeters of penetration capability, focused into a jet of superheated metal and explosive force. The interior of the Sherman transformed into an inferno as 75 millimeter main gun rounds cooked off in a chain reaction that tankers had learned to call brewing up. The name was darkly humorous, suggesting tea preparation rather than the reality of men burning alive inside a steel coffin. Hardesty and his crew tumbled out of hatches onto French soil that had already swallowed 847 American tanks in just 35 days of fighting since D-Day. He hit the ground hard, rolled behind the burning wreck, felt the heat on his face from 15 meters away, and watched through shimmering waves of superheated air as 2 more Shermans from his platoon attempted the same suicidal climb over the same impassable hedgerow. Both tanks exposed their vulnerable undersides at the apex of their climb. Both tanks were hit by Panzerfaust rounds fired from concealed positions. Both tanks burned with the characteristic orange-black smoke that marked American tank losses across Normandy. 3 tanks destroyed in 4 minutes, 9 men killed or wounded, and the hedgerow stood untouched, unconcerned, as ancient and immovable as the day the first Norman farmer had piled dirt and stones around his field boundaries, sometime around the year 1347. This was the mathematics of hell that nobody had anticipated during the months of meticulous D-Day planning, conducted in the map rooms and planning cells of Supreme Headquarters Allied Expeditionary Force. The Normandy bocage country contained an estimated 40,000 kilometers of hedgerows, each one an earthen wall topped with vegetation so dense that standard military maps couldn't accurately represent their defensive value. Allied intelligence officers had dismissed them as agricultural boundaries, minor obstacles that tanks would simply push through en route to the German-held interior of France. They had studied aerial photographs, consulted pre-war agricultural surveys, and concluded that hedgerows were merely thick bushes on small dirt mounds that would pose no significant impediment to armored operations. They were catastrophically, lethally wrong. The reality that greeted American forces as they pushed inland from the beaches was something that pre-war planners had failed to comprehend. Each hedgerow was an earthen fortress, constructed over centuries through the simple agricultural practice of clearing fields and piling the stones and dirt at the boundaries. Generation after generation of Norman farmers had added to these barriers, and over 400 years they had grown into walls of packed earth, reinforced by root systems from oak, elm, and hawthorn trees that had created a natural rebar of organic fiber stronger than anything engineers could design. The vegetation on top, dense, thorny undergrowth that grew to heights of 3 to 4 meters, created a visual barrier that prevented observation and concealed defensive positions. The Germans, masters of defensive warfare, had recognized the bocage's potential immediately and turned each field into a killing zone. Private First Class Curtis Cullen, 19 years old, farm boy from Cranberry, Tennessee, crouched in a roadside ditch 200 meters behind the burning Shermans and watched the horror unfold with an expression that his squad mates would later describe as thinking too hard, like he does. Cullen was a mechanic with the 2nd Armored Division, specifically assigned to A Company of the 41st Armored Infantry Regiment, and his official job description was keeping half-tracks, jeeps, and support vehicles operational under field conditions. What made him different from the 19,000 other mechanics scattered across the European theater of operations was simple. Curtis Cullen couldn't stop thinking about problems even after everyone else had accepted them as unsolvable facts of life. His mind worked like the machinery he repaired, constantly analyzing systems, identifying failure points, and imagining modifications that might improve performance. The hedgerow problem had been eating at him for 37 days, ever since his regiment had pushed inland from Omaha Beach on June 7th and encountered the first of these earthen fortifications in the fields south of Vierville-sur-Mer. He had watched tanks try to bull through hedgerows head-on, engines roaring at maximum RPM, tracks churning mud and vegetation, getting absolutely nowhere because the resistance was too evenly distributed across the tank's front. He had watched tanks try to climb over the barriers, exposing their thinly armored bellies at the top of the climb, getting killed by German Panzerfaust teams who had learned to wait for that exact moment of vulnerability. He had watched combat engineers blow gaps using Bangalore torpedoes and satchel charges, a process that took 40 minutes per hedgerow, consumed scarce explosives, and announced American intentions to every German defender within 2 kilometers. And he had watched American casualties mount to numbers that made the D-Day beach landings look like a warm-up exercise. The statistics were classified at the division level and above, but Cullen had ears, and he talked to the medics and Graves registration personnel who handled the results of failed attacks. First Army had suffered approximately 40,000 casualties in 6 weeks of bocage fighting, a rate that exceeded planners' worst-case projections by a factor of 3. Tank losses were running at 847 vehicles destroyed or disabled, exceeding replacement rates by 340%, and threatening to leave American armored divisions immobilized for lack of equipment. Forward progress was measured in meters per day, rather than the kilometers that pre-invasion plans had anticipated. The original D-Day schedule had called for American forces to reach Avranches, 90 kilometers inland, by June 25th. It was now July 11th, 16 days behind schedule, and the front lines had advanced barely 30 kilometers from the beaches. The Germans, outnumbered by ratios approaching 3-to-1 in most sectors and outgunned by every objective measurement of artillery and air support, were using the hedgerows as ready-made fortifications that multiplied their defensive effectiveness by factors that military analysts would later calculate at somewhere between 8 and 12. A single German infantry squad, 9 men with rifles, 1 MG-42 machine gun, and 2 Panzerfaust anti-tank weapons, could hold a hedgerow junction against an entire American tank platoon of 5 Shermans and 60 supporting infantry because the terrain simply wouldn't allow the Americans to bring their superior numbers to bear. The fields were too small, typically 50 to 100 meters on a side, creating kill zones where German defenders could engage American armor at point-blank range with near certainty of success. Curtis Cullen had grown up on a 140-acre farm in eastern Tennessee, where the primary crop was trouble and the secondary crop was whatever would grow in rocky soil that agricultural professionals had abandoned as commercially unviable. His father, James Cullen, had owned exactly one tractor, a 1936 Farmall F-20 with a worn-out engine and transmission held together by improvisation, that broke down every third day and required young Curtis to fabricate replacement parts from whatever scrap metal could be scavenged from neighboring properties, abandoned mining equipment, or the county junkyard 15 miles down unpaved roads. By age 14, Curtis could look at a broken mechanism, understand the mechanical principles that governed its operation, diagnose why it had failed, and improvise a solution using tools and materials that would make a trained engineer weep with frustration or admiration depending on their temperament. The Army had spotted this talent immediately during basic training at Fort Knox, Kentucky, where Cullen had repaired a broken tank transmission using a hammer, 3 feet of wire, and a replacement gear he'd machined from a piece of scrap steel in the motor pool shop. His company commander had written on his evaluation, "This soldier possesses an intuitive understanding of mechanical systems and an ability to improvise solutions under field conditions that exceeds anything I have observed in 16 years of service." The Army had promptly assigned him to mechanized maintenance with the 2nd Armored Division, where his ability to keep vehicles running with baling wire, optimism, and mechanical intuition had earned him 3 field commendations and the unofficial title among his fellow mechanics of "that hillbilly who can fix anything the Army manages to break." But the hedgerow problem wasn't about fixing something that was broken. Standard Army equipment, Shermans, half-tracks, jeeps, artillery pieces, all functioned perfectly well according to their design specifications. The problem was that these vehicles had been designed for a different kind of warfare, envisioned fighting across the relatively open terrain of Belgium and Germany, and nobody had seriously contemplated fighting through the unique nightmare of bocage country, where ancient agricultural engineering had created defensive terrain more formidable than anything military engineers could design. The tanks worked fine. The terrain was impossible. This was about modifying equipment that worked perfectly well in every environment, except this specific hell of Norman field boundaries that stretched across 40,000 kilometers of French countryside. The breakthrough, or at least the beginning of the breakthrough, came at 03:12 hours on July 13, 1944, in circumstances that Cullen would later describe with characteristic Tennessee understatement as not ideal for thinking clearly about mechanical problems. He was crouched in a shell crater 30 meters from a knocked-out German Panther tank, waiting for dawn, and contemplating the various ways he might die in the next 12 hours, when his shielded flashlight beam swept across something glinting in the mud at the bottom of the crater, a piece of German steel, twisted and sharp-edged, about 8 inches long and curved like a scythe blade or a question mark. It had been part of the Panther's track assembly before American artillery had blown the 45-ton vehicle into its component pieces during the previous day's fighting. Cullen picked it up, felt the weight of high-quality German steel in his hand, noticed how the curve created a natural cutting edge, ran his thumb along the sharp side and drew blood, and in that moment of minor pain, something clicked in his mind. The hedgerows weren't solid barriers like concrete walls. They were compressed masses of earth and vegetation held together by root systems. If you hit them straight on with a blunt surface like a tank's glacis plate, the force distributed across the entire front and nothing penetrated. But if you concentrated force into sharp edges, like plow blades cutting furrows, like scythes cutting wheat, like this piece of curved German steel that had just sliced his thumb, you could cut through the roots that held everything together. The earthen wall would collapse from its own weight, the tank could drive through the gap, and the entire operation would take maybe 30 seconds instead of 40 minutes. No exposed belly armor, no vulnerable climb, no warning to German defenders. Just straight-through penetration using nothing more complex than sharp steel and 33 tons of forward momentum. Kuhlen's hands were shaking, from cold, from adrenaline, from excitement, as he pulled out his notebook and sketched the concept using a pencil stub and the faint light of his shielded flashlight. Two prongs extending forward from the tank's lower glacis plate, each prong made from steel rail sections or structural girders, each prong sharpened to a point and angled slightly outward to cut two parallel furrows through the hedgerow's base. Weld them solid to the hull using the same techniques the Army already employed for attaching spare track links and other field modifications. Position them at ground level so they dig into the earth like plow blades. Let the Sherman's 500 horsepower engine and 33 tons of mass provide the cutting force. The entire modification would require perhaps 50 pounds of scrap steel per tank, an afternoon's work by a competent welder with access to a cutting torch, and materials that were literally lying around every battlefield in Normandy in the form of destroyed vehicles, knocked out German beach obstacles, and abandoned construction steel. He spent the remaining hours until dawn refining the concept in his mind, working through potential failure modes, calculating approximate angles and weights. The prongs needed to be strong enough to withstand the cutting force without bending or breaking. That meant solid steel at least 2 inches thick, probably structural beam sections if he could find them. They needed to be positioned low enough to dig into the base of the hedgerow where the root systems were strongest, but high enough that they wouldn't catch on uneven ground and stop the tank. They needed to be angled outward slightly, maybe 15 degrees from vertical, to create a cutting action rather than just pushing dirt forward. And they needed to be removable, or at least not interfere with normal tank operations when not actively cutting through hedgerows. The sun rose at 05:47 hours on July 13, 1944, revealing a battlefield littered with destroyed armor and dead men, the aftermath of another failed American attack against German defensive positions anchored on hedgerow lines. Curtis Kuhlen emerged from his shell crater carrying a mud-stained notebook full of sketches and an idea that would, within 2 weeks, save thousands of American lives and break the stalemate that had paralyzed the Normandy campaign for 37 days. But first he had to convince somebody, anybody, to listen to a 19-year-old farm boy mechanic with dirt under his fingernails, no formal engineering education, and a Tennessee accent so thick that officers from New York and Massachusetts sometimes pretended not to understand him just to avoid the effort of translation. His first attempt at selling the idea came at 0630 hours when he approached his immediate supervisor, Technical Sergeant Robert Morrison, who was coordinating repair efforts on 3 half-tracks damaged during the previous day's fighting. Kuhlen explained the concept using his sketches and hand gestures. Morrison listened politely for about 90 seconds before cutting him off with words that Kuhlen would remember for the rest of his life. "Private, we got real problems to solve here, not science experiments to run. You want to help? Get that half-tracks transmission back together before the captain asks why we're down 3 vehicles." The dismissal stung, but Kuhlen had grown up being underestimated by people who confused educational credentials with intelligence. He went back to work on the half-track transmission, but the idea wouldn't leave his mind. His second attempt came at 11:37 hours, when he managed to corner Lieutenant James Everett, a platoon leader with A Company who had a reputation for listening to enlisted men's suggestions. Everett was more receptive than Morrison had been, studied the sketches, asked intelligent questions about structural strength and welding techniques, but ultimately he shook his head and said, "Kuhlen, I appreciate the initiative, but this is above my pay grade. Ordnance Department designs tank modifications, not farm boys from Tennessee. No offense intended." Kuhlen replied that none was taken, which was technically true but emotionally generous, and returned to his assigned duties while his brain continued working the problem from every angle he could imagine. The breakthrough, the real breakthrough, not just the mechanical insight, but the human connection that would turn an idea into reality, came at 16:23 hours when Cullen encountered Sergeant John Willard from B Company, 702nd Tank Battalion, sitting on the ground next to his disabled Sherman with an expression of profound despair. Willard's tank had thrown a track during an attempted hedgerow crossing, and he was waiting for recovery vehicles to tow the 33-ton beast back to the repair depot. Cullen knew Willard slightly from previous maintenance interactions, knew him as a smart tanker who'd survived 31 days of combat through a combination of skill, luck, and extreme caution about which hedgerows to attack. Cullen sat down next to him without invitation and said, "Sergeant Willard, I got an idea for the hedgerow problem. You got 5 minutes to listen before you tell me I'm crazy?" Willard looked at him with tired eyes and said, "Private, I got nothing but time until the recovery truck shows up. And crazy ideas are better than no ideas, which is what we got now." So Cullen explained the concept using his sketches and the piece of German steel he'd kept in his pocket as a talisman. He described the physics of cutting through root systems, the mechanics of welding steel prongs to tank hulls, the tactical advantage of being able to penetrate hedgerows in 30 seconds instead of 40 minutes. He talked for 6 minutes, not 5, and when he finished, Willard was staring at him with an expression that combined hope, skepticism, and something approaching reverence. "Kid," Willard said, using the informal term that tankers reserved for people they actually respected, "that might actually work, but we need to test it before we take it up the chain of command, because if it fails spectacularly, we'll both look like idiots, and you'll be back doing real work instead of playing inventor." Cullen agreed immediately. They needed a prototype, and they needed it fast, before the idea got buried in bureaucratic channels or somebody else claimed credit for the concept. Willard knew where to find the necessary materials: a destroyed German beach obstacle made of steel railway sections, abandoned on the road 2 kilometers back. They could cut what they needed using the battalion's cutting torches, weld the pieces to Willard's tank once it got back to the repair area, and test the modification the next day during regular combat operations. The welding torch hissed blue-white flame against German steel at 08:47 hours on July 14, 1944, and Curtis Cullen felt the familiar weight of doubt pressing against his chest like a physical force. The steel railway section, salvaged from a destroyed German beach obstacle 3 kilometers back toward Omaha Beach, was harder than anything he'd worked with before. High-carbon steel that the Germans had used to stop landing craft from reaching the shore. Now he was cutting it into 4-foot sections using a borrowed oxyacetylene torch, while Sergeant John Willard's tank crew watched with expressions ranging from curious optimism to outright skepticism. The repair depot behind the village of LeCambre was a chaos of damaged vehicles, exhausted mechanics, and the constant background noise of artillery fire from positions 5 kilometers south. Nobody paid attention to one more private cutting scrap metal, which was exactly what Cullen wanted. If this modification failed during testing, he preferred that failure to be witnessed by as few people as possible. The cutting took 43 minutes, and by the time Cullen finished, he had 4 steel prongs, each one measuring 48 inches long, 6 inches wide, and 2 inches thick. German engineering had made them nearly indestructible, which was precisely what this application required. He'd shaped the ends into rough points using an angle grinder, creating cutting edges that would concentrate force into the hedgerow's root system. The prongs weighed approximately 35 pounds each, and when all 4 were welded to Willard's Sherman, the total added weight would be roughly 140 pounds, negligible for a vehicle that already massed 33 tons. Cullen laid out the steel sections on the ground in front of Willard's tank and stepped back to visualize the final configuration. Two prongs would mount on the lower glacis plate angled slightly outward, positioned to cut parallel furrows through the hedgerow's base. Two more prongs would mount slightly higher and further apart, creating a four-point cutting pattern that would slice through root systems from multiple angles simultaneously. Sergeant Willard approached and studied the layout with a tanker's eye for practical problems. "Those lower prongs are going to dig into the ground every time I cross uneven terrain," he said, pointing at the configuration Cullen had sketched. "I'll be plowing French soil instead of driving through it." Cullen had already considered this issue during his night in the shell crater. "We angle them up slightly, maybe 10 degrees from horizontal," he replied, adjusting the prong positions to demonstrate. "They'll ride just above ground level on flat terrain, but dig in when you hit a hedgerow and the nose starts to climb. The tank's weight will force them down into the earth." Willard nodded slowly, working through the physics in his mind. "And when I'm not attacking hedgerows, they'll stick out in front like tusks and catch on everything." "That's a problem we can solve later," Cullen said. "Right now we just need to prove the concept works. If it does, we'll figure out how to make the prongs removable or retractable." The welding began at 8:09:34 hours and immediately revealed problems that Cullen's theoretical planning hadn't anticipated. The Sherman's glacis plate was rolled homogeneous armor, designed to deflect projectiles, and it resisted welding with a stubbornness that matched its battlefield purpose. The first weld Cullen attempted cracked almost immediately as the heat-affected zone cooled and contracted. He tried again with more preheat, running the torch along the joint line to bring the base metal up to temperature before striking the welding arc. This time the weld held, but barely, and Cullen realized with growing concern that his farm boy welding skills might not be adequate for this application. The stress these prongs would experience during hedgerow cutting would be immense, potentially several tons of force concentrated into the weld joints. If those joints failed during combat, the prongs would shear off, and the tank would be stuck halfway through a hedgerow with German anti-tank teams closing in. Technical Sergeant Robert Morrison, the same supervisor who dismissed Cullen's idea 24 hours earlier, appeared at 10:15 hours and watched the welding operation with professional interest. "Private Cullen," he said, after 3 minutes of silent observation, "you're going to kill Sergeant Willard when those welds fail and his tank gets stuck in a hedgerow with Panzerfausts incoming." Cullen shut off his welding rig and faced Morrison directly. "Sergeant, you got a better welding technique, I'm listening. You want to tell me again to work on real problems instead of science experiments? I'm listening to that too. But somebody needs to solve this hedgerow situation before we lose another 100 tanks and 1,000 men." Morrison stared at him for a long moment, then said something that changed everything. "Move aside, farm boy. Let me show you how the Army actually welds armor plate." For the next 2 hours, Morrison taught Cullen techniques that weren't in any manual, but had been passed down through generations of military welders. How to preheat armor plate using a rosebud torch tip to expand the heat-affected zone. How to run multi-pass welds with specific rod angles that created fusion deep into the base metal. How to peen each weld pass with a hammer while the metal was still hot, compressing the weld and reducing residual stress. How to build up weld joints in layers that would flex slightly under load rather than cracking. By 12:15 hours, they had all 4 prongs welded solidly to Willard's tank, and Morrison stepped back to inspect their work with the critical eye of a craftsman who'd spent 14 years joining metal. "It'll hold," he said finally. "Might not be pretty, but it'll hold. Now let's see if your crazy idea actually works." The first test took place at 14:47 hours on July 14, 1944, in a field 2 kilometers south of La Cambe, with an audience that had grown from Willard's 5-man crew to nearly 40 soldiers who'd heard rumors that some hillbilly mechanic built a hedgerow-busting contraption. The target was a hedgerow of average height, approximately 4 meters tall, that separated two fields and had been surveyed by engineers as typical of the obstacles facing American forces across a 40-kilometer front. German forces had been cleared from this particular section 2 days earlier, which meant the test could proceed without enemy interference, but also meant there would be witnesses if the modification failed spectacularly. Kulin stood 50 meters back from the hedgerow and felt his stomach twist into knots as Willard's Sherman rumbled forward at 8 kilometers per hour, engine roaring, the four steel prongs extending forward like tusks on some mechanical beast. The tank hit the hedgerow at 14:48 hours and 23 seconds, and for one horrible moment, nothing seemed to happen. The prongs buried themselves into the earthen base. The tank's nose began to climb, and Kulin thought with sinking certainty that his modification was going to fail in front of 40 witnesses, and he'd spend the rest of the war being reminded of his hubris. Then, physics took over. The prongs cut through the root system like scythe blades through wheat stalks, the concentrated force shearing centuries-old oak and elm roots that had held the hedgerow together since before America was a nation. The earthen wall collapsed from its own weight as its structural integrity failed, vegetation tumbling forward, and the Sherman crashed through the gap in a shower of dirt and vegetation that covered the tank in a brown-green camouflage nature had never intended. Total elapsed time from initial contact to complete penetration, 28 seconds. The silence that followed lasted perhaps 3 heartbeats before somebody started cheering, and then the entire crowd erupted in shouts and applause that could probably be heard by German positions 5 kilometers away. Willard backed the tank through the gap he'd created, turned around, and attacked the same hedgerow from the opposite direction, cutting through in 31 seconds. He attacked a third time at an angle, demonstrating that the modification worked regardless of approach vector. After the third successful penetration, Willard climbed out of his tank with an expression that combined vindication, relief, and something approaching religious ecstasy. He grabbed Kulin in a bear hug that lifted the smaller man off the ground and shouted, "Kid, you just saved the entire fucking invasion." Kulin, who'd been raised in a Baptist household where profanity was discouraged, decided that some circumstances warranted exception to social norms. Word spread through the 2nd Armored Division with the speed that only truly important information achieves in military organizations. By 1600 hours, Captain James Roberts from Willard's company had witnessed a demonstration and was drafting a report for battalion headquarters. By 1800 hours, Lieutenant Colonel Edwin Crable from the 702nd Tank Battalion had watched Willard's tank cut through 6 different hedgerows and was composing an urgent message to Division Command. By 2100 hours, Major General Edward Brooks, commanding officer of the 2nd Armored Division, was reading reports from 3 different sources about a hedgerow cutting device developed by an enlisted mechanic using scrap metal and field welding. Brooks, who'd been fighting the bocage nightmare for 37 days and watching his tank strength bleed away at unsustainable rates, did something that would prove decisive. He picked up a field telephone and called General Omar Bradley's headquarters directly. General Omar Bradley, commanding officer of 1st Army and one of the architects of the Normandy invasion, arrived at the 2nd Armored Division's command post at 09:15 hours on July 15th with an entourage of staff officers and an expression that suggested deep skepticism about miracle solutions to intractable problems. Bradley was a professional soldier who'd spent his career being promised technological breakthroughs that failed to deliver, and he approached Kulin's modification with the same cautious pessimism he applied to all field innovations. The demonstration took place at 09:47 hours in the same field where Kulin had conducted his first test, but this time the audience included 2 general officers, 4 colonels, a dozen staff officers, and a Life magazine photographer who'd been embedded with 1st Army headquarters to document the Normandy campaign. Willard's tank, now officially designated as the test platform for what was being called the Kulin Cutter, by soldiers who understood the importance of attributing innovations to their inventors, approached the hedgerow at Bradley's signal. The Sherman hit the earthen barrier at 1,800 RPM engine speed. The steel prongs bit into soil and roots, and 28 seconds later the tank emerged on the opposite side, trailing vegetation like some prehistoric creature rising from a swamp. Bradley watched a second demonstration, then a third, then walked over to examine the steel prongs with the attention to detail that had made him one of America's most effective field commanders. He ran his hand along one of the cutting edges, studied the weld joints, looked at Kulin standing nervously nearby, and asked the question that would determine whether this innovation died as an interesting experiment or became standard equipment for every American tank in Normandy. "Private Kulin," Bradley said, "can this modification be manufactured and installed on 500 tanks in the next 7 days?" Kulin, who'd spent his life understanding that the difference between success and failure often came down to promising only what you could deliver, took a breath and did quick calculations in his head. Each modification required 4 steel prongs, approximately 140 pounds of steel total, plus welding time of maybe 4 hours per tank with experienced welders. The steel was readily available from German beach obstacles that littered the Normandy coast. The enemy had helpfully provided thousands of tons of high-quality steel in the form of anti-landing craft barriers that were now useless since the invasion had succeeded. The welding could be done by mechanics and welders already present in the division, assuming they were pulled from other duties. The real constraint was time. 7 days to manufacture 500 modifications meant completing roughly 70 tanks per day, which meant running welding operations 24 hours a day, using every available welder and cutting torch. "Sir," Cullen replied, "we can do it in 5 days if you give me authority to requisition materials and personnel." Bradley smiled for the first time since arriving at the demonstration. "You have that authority as of this moment, Private, and you're promoted to Sergeant Effective immediately, because I need somebody with rank to coordinate this operation, and you're the only person who completely understands what needs to be done." He turned to his staff officers and began issuing orders with the machine gun rapidity that characterized his command style. First Army would provide welding teams from 3 armored divisions. Ordnance units would begin cutting German beach obstacles into prong sections immediately. Engineers would survey available steel and designate priority locations for harvesting material. And the entire operation would proceed under absolute priority, superseding all other maintenance activities except those required to keep tanks operational for immediate combat. The production line began operating at 1400 hours on July 15, 1944, in a field behind the village of Colombière, where the 2nd Armored Division had established its rear maintenance area. Kulin had transformed from individual inventor to production manager in the space of 6 hours, a transition that would have been overwhelming, except that he'd spent his teenage years managing a farm that ran on improvisation and determination. He organized the operation like an assembly line, with specialized stations for each step of the manufacturing process. Station 1. Cutting teams using oxyacetylene torches to section German railway steel into 4-foot prongs. Station 2. Grinding teams using angle grinders to shape cutting edges and remove slag. Station 3. Fitting teams that positioned prongs on tanks and marked weld locations. Station 4. Welding teams that performed the actual attachment using the techniques Morrison had taught. Station 5. Inspection teams that tested weld quality and structural integrity. The first modified tank rolled out of the production line at 1823 hours after 4 hours and 23 minutes of work. Too slow, Kulin thought, doing math in his head. At that rate, they'd complete maybe 120 tanks in 7 days, nowhere near the 500 that Bradley had requested. He walked the production line looking for bottlenecks, watching each station with the analytical eye he'd developed, watching farm machinery operate. The cutting station was fine. They had 8 torch teams working simultaneously and could section prongs faster than the welders could attach them. The grinding station was keeping up adequately. The fitting station was slowing everything down because positioning the prongs required precision, and precision required time. And the welding station, despite having 12 welders working in shifts, was the real constraint because each tank required approximately 3 hours of actual welding time, and that couldn't be rushed without compromising weld quality. Cullen made adjustments throughout the night, implementing improvements that increased production efficiency in ways that would have impressed industrial engineers. He standardized the prong positioning by creating templates, wooden jigs, that welders could use to position prongs identically on every tank without measuring each time. He organized welding teams into pairs so that experienced welders could supervise less experienced personnel and maintain quality while increasing throughput. He established a night shift that worked under portable lighting, keeping the production line running 24 hours a day instead of shutting down after dark. By 0800 hours on July 16th, the production line had completed 23 tanks in 18 hours of operation. Still not fast enough, but accelerating. The breakthrough in production efficiency came from an unexpected source at 1134 hours on July 16th, when a welder named Robert Patterson from the 3rd Armored Division suggested a modification to Cullen's modification. Instead of welding 4 separate prongs to each tank, Patterson proposed welding the prongs to a steel framework that could be bolted to the tank's lower hull, using existing mounting points designed for spare track links and other external equipment. This approach would reduce welding time per tank from 3 hours to approximately 45 minutes for the framework assembly, plus another 30 minutes for bolting the completed framework to the tank. The total time per tank would drop from over 4 hours to roughly 90 minutes, and the modification would become removable, solving the problem Willard had identified about the prongs interfering with normal operations. Cullen recognized genius when he heard it, and immediately reorganized the production line around Patterson's concept. The new process created prefabricated frameworks at a central assembly station where welders could work on benches rather than crawling around tanks. The completed frameworks were then transported to tanks and bolted in place by installation teams using standard wrenches and bolts. The first framework-based modification was completed at 14 to 22 hours and tested immediately on a nearby hedgerow with complete success. By 1800 hours on July 16th, the reorganized production line was completing tanks at a rate of 1 every 52 minutes. Cullen did the mathematics and felt a surge of relief. At that rate, they could complete 500 tanks in just under 11 days, still not meeting Bradley's 7-day requirement, but close enough that they'd have substantial numbers ready when the next major offensive launched. The production statistics told a story of American industrial capacity translated to battlefield conditions. Between July 15th and July 25th, 1944, a span of 10 days, the improvised production line manufactured and installed 564 Cullen cutters on Sherman tanks, tank destroyers, and other armored vehicles across 3 divisions. The operation consumed approximately 78 tons of German steel from beach obstacles, employed 340 welders working in rotating shifts, used 1,247 cutting torch tips, and generated enough metal grinding dust to fill 6 cargo trucks. The cost per modification, calculated by Ordnance Department accountants who tracked such things, came to exactly $11.73 in materials and labor. Though soldiers preferred the more dramatic figure of 12 cents worth of scrap steel, ignoring the labor costs, because the welders were getting paid regardless of what they were welding. The tactical impact became apparent during Operation Cobra, the breakout offensive that began on July 25, 1944, with the largest aerial bombardment in military history, followed by armored exploitation through German defensive lines. The modified tanks transformed bocage warfare from a nightmare of slow advances and heavy casualties into mobile operations that resembled the pre-invasion planning scenarios. Instead of spending 40 minutes to breach each hedgerow while German defenders adjusted their positions and called in artillery, American armor crashed through in 30 seconds and kept moving before the enemy could react. The psychological impact on German defenders was almost as important as the tactical advantage. Soldiers who'd grown comfortable using hedgerows as nearly impregnable fortifications suddenly found American tanks appearing in their defensive positions with terrifying speed. The first large-scale combat test occurred at 11:47 hours on July 26th, when Combat Command A of the 2nd Armored Division attacked German positions south of St. Gilles using 78 tanks equipped with Kulin cutters. The after-action report, filed by Colonel Maurice Rose and preserved in the National Archives, described results that exceeded the most optimistic predictions. The combat command advanced 11 kilometers in 6 hours, crossing an estimated 214 hedgerows, without losing a single tank to the belly armor vulnerability that had characterized previous bocage fighting. German defenders, anticipating the usual slow American advance, were overrun before they could adjust their defensive tactics. By 1800 hours on July 26th, Combat Command A had penetrated deeper into German territory than any American unit had advanced in the previous 37 days of fighting. The numbers from Operation Cobra's first week told a story of transformation. American tank losses dropped from an average of 23 tanks destroyed per day during June and early July to fewer than 8 tanks destroyed per day in the last week of July. The reduction came almost entirely from eliminating the belly armor vulnerability that had made hedgerow climbing suicidal. German anti-tank teams, trained to wait for tanks to expose their undersides while climbing hedgerows, found themselves facing tanks that simply crashed through at ground level and emerged shooting before defensive positions could be adjusted. The tactical advantage translated into strategic results. By July 30th, American forces had broken through the German defensive crust that had contained the invasion for 54 days, and Patton's Third Army was racing toward Brittany through gaps that bocage terrain had previously made impossible. The human cost, or rather the human cost avoided, could be measured in multiple ways. During the 37 days of fighting before Kulin cutters became available, American forces in the bocage sector suffered approximately 40,000 casualties while advancing 30 kilometers. During the 11 days of Operation Cobra's initial phase with Kulin cutters in widespread use, American forces suffered approximately 8,000 casualties while advancing 90 kilometers. The difference, roughly 32,000 casualties avoided by eliminating the need for slow, costly hedgerow assaults, represented one of the highest returns on investment for any field modification in military history. If Kulin's modification saved even a fraction of those potential casualties, the impact was measured in thousands of lives, tens of thousands of wounded soldiers who avoided injury, and countless families who received their sons and husbands home instead of receiving folded flags. The German perspective on Kulin cutters emerged from captured documents and prisoner interrogations conducted during late July and early August. A report from the German 7th Army, captured after the Falaise pocket collapsed, noted with understated alarm that American armor has developed new capability to penetrate bocage defenses with unexpected speed. Previous defensive tactics, assuming slow American advance, require immediate revision. A captured German tank commander, interviewed on July 31st, provided more colorful assessment. We were told the Americans couldn't handle the hedgerows, that we could hold them forever using the terrain. Then one morning their tanks started cutting through like knives through butter, and we realized everything had changed. You can't fight enemies who solve problems that fast. Curtis Kulin's personal experience during this period represented a peculiar form of military success. He'd created something so important that he was immediately pulled away from seeing its full impact. On July 18th, 3 days into the production operation, he was summoned to First Army headquarters, where General Bradley wanted him to brief staff officers on the modification's technical details. On July 22nd, he was photographed by Life magazine demonstrating the cutting process, images that would appear in the August 14th issue under the headline, "Farm Boy's Invention Breaks the Hedgerow Stalemate." On July 27th, he was awarded the Legion of Merit, an honor typically reserved for field-grade officers, in a ceremony that felt surreal to a 19-year-old who'd been expecting to spend the war fixing half-track transmissions. Through all of this, other soldiers were using his modification to fight battles he could only hear about through second-hand reports and after-action summaries. The production of Kulin cutters continued through August and into September, as armored divisions in other sectors of Normandy requested the modification for their tanks. By September 1, 1944, when the Normandy campaign effectively ended with American forces reaching the German border, a total of 1,247 Kulin cutters had been manufactured and installed on Sherman tanks, tank destroyers, and armored recovery vehicles. The modification spread beyond American forces. British armor units fighting in the bocage sector requested and received approximately 200 cutters for their Churchill and Cromwell tanks, though the different hull configurations required design modifications that Kulin helped develop during a 3-day visit to British lines in mid-August. The long-term impact extended far beyond the Normandy campaign. The Kulin cutter demonstrated that field modifications developed by ordinary soldiers could solve problems that engineering staffs and military bureaucracies had failed to address. This lesson influenced American military thinking about innovation and led to formal programs for evaluating soldier-developed improvements to equipment and tactics. The Army established the Armored Force Board in September 1944 specifically to test and evaluate field modifications, with Kulin cutters cited as the primary example of why such programs were needed. The board eventually evaluated 417 different modifications proposed by soldiers, adopting 89 of them for widespread use and potentially saving thousands of additional casualties through improvements to equipment, tactics, and procedures. The statistical accounting of Kulin cutter effectiveness, compiled by Army historians in the years after the war, provided numbers that captured both the tactical and strategic value. Tanks equipped with Kulin cutters achieved hedgerow penetration in an average of 31 seconds compared to 38 minutes for conventional breaching methods using explosives or bulldozers. The modification reduced tank losses during hedgerow crossing by approximately 89% by eliminating the belly armor exposure that had made climbing suicidal. The faster tempo of operations enabled by rapid hedgerow crossing allowed American forces to advance an estimated 60 kilometers further during Operation Cobra than would have been possible using conventional tactics. And the psychological impact on German defenders, though impossible to quantify precisely, contributed to the collapse of German defensive cohesion during the final week of July, when commanders realized that hedgerows no longer provided the defensive advantage their planning had assumed. The ultimate irony was that the steel used to manufacture Kulin cutters came from German beach obstacles, the Atlantic Wall defenses that were supposed to prevent the Allied invasion from ever reaching the beaches, the same German engineering that had created formidable anti-landing craft barriers provided the high-quality steel that broke the bocage stalemate and enabled the breakout from Normandy. Curtis Kulin, when asked about this irony by a reporter in August 1944, displayed the dry humor that characterized his public statements. Seemed wasteful to leave all that good steel lying on the beach when we had use for it. The Germans probably would have appreciated us recycling their materials, being efficient and all. The recognition Kulin received during and after the war followed the unpredictable pattern that governs military fame. He was promoted to sergeant, then to staff sergeant, then to technical sergeant by October 1944, rising 5 ranks in 4 months based on a single innovation. He received the Legion of Merit in July, the Bronze Star in September, for meritorious service in support of combat operations, and was mentioned by name in General Bradley's after-action report on Operation Cobra. Life magazine featured him in a 4-page spread complete with dramatic photographs of Kulin cutters in action, and a profile that presented him as the epitome of American ingenuity under pressure. Yet he remained fundamentally uncomfortable with fame, preferring to work on vehicles rather than attend ceremonies, and repeatedly attempting to return to his original assignment as a mechanic with the 41st Armored Infantry Regiment. The fate of the original prototype, Sergeant Willard's Sherman tank, with the first Kulin cutter welded directly to its hull, illustrated the tension between historical preservation and military necessity. The tank continued operating through Operation Cobra, accumulated 847 kilometers on its odometer during the breakout, and was finally knocked out by German anti-tank fire near Mortain on August 7th during the German counteroffensive. Willard and his crew survived by bailing out seconds before a Panzerfaust hit transformed their tank into another burning wreck in a war that consumed equipment at rates that made individual vehicles meaningless. The historical significance of that particular tank, the first to successfully demonstrate a modification that changed the course of the Normandy campaign, was lost in the general destruction, and no effort was made to preserve or recover it. The war moved too fast for such sentimentality. Curtis Kulin survived the war, mustered out of the Army in November 1945 with the rank of Master Sergeant, and returned to Tennessee where he used his GI Bill benefits to attend a technical school and eventually opened an automotive repair shop in Knoxville. He married in 1947, fathered 3 children, served on the local school board, and generally lived the quiet life that characterized millions of veterans who'd done extraordinary things during the war and returned to ordinary existence afterward. He rarely spoke about his wartime experiences except when directly asked, and even then he tended to deflect attention toward other soldiers who'd used his modification in combat rather than dwelling on his own role in its creation. The Kulin cutter itself passed into military history as an example of field innovation at its best. A simple solution to a complex problem, developed by an ordinary soldier under combat conditions, manufactured using improvised methods and scrap materials, and deployed with devastating effectiveness against an enemy who'd grown comfortable with terrain-based defensive advantages. Military historians studying the Normandy campaign invariably cite the Kulin cutter as one of the key factors that enabled the breakout from the bocage, ranking it alongside air superiority and artillery support as decisive tactical advantages that translated into strategic victory. The modification appears in textbooks, documentaries, and museum displays as the quintessential example of American problem-solving under pressure. The final accounting of lives saved by the Kulin cutter remains necessarily approximate, because historians cannot definitively calculate what casualties would have occurred in the absence of the modification. The conservative estimate, based on casualty rates during pre-Cobra bocage fighting extrapolated across the 11 days of the initial breakout, suggests that Kulin's innovation prevented approximately 4,200 American casualties, killed, wounded, or captured, during Operation Cobra alone. Additional casualties were almost certainly avoided during subsequent operations in August and September, as modified tanks continued operating in terrain where hedgerows remained tactically significant. The number of German casualties directly attributable to Kulin cutters is even harder to calculate, but after-action reports document at least 67 German tanks destroyed by American armor that used Kulin cutters to achieve tactical surprise during the breakout period. These numbers, 4,200 American lives saved, 67 German tanks destroyed, 1,347 modifications manufactured, 11 days of decisive combat operations, tell the quantifiable story of what Curtis Kulin's invention accomplished. But numbers alone cannot capture the human reality of soldiers who survived battles they would have died in, families who welcomed home veterans who might have been buried in France, and a campaign that succeeded in breaking a stalemate that had threatened to turn the Normandy invasion into a bloody stalemate reminiscent of World War I's Western Front. The real impact lived in the individual moments when tanks crashed through hedgerows in 28 seconds instead of 40 minutes, when German defensive positions were overrun before defenders could react, when American soldiers advanced with confidence instead of the grinding fear that had characterized bocage fighting during June and early July. The story of the Kulin Cutter is ultimately about seeing solutions where others saw only problems, about having the courage to propose ideas when conventional wisdom insisted they wouldn't work, and about the democratic nature of innovation that allowed a 19-year-old farm boy with dirt under his fingernails to change the course of history. Curtis Culin didn't have formal engineering education, didn't have access to sophisticated design tools or testing facilities, didn't have institutional authority or military rank to command resources. What he had was mechanical intuition, developed through years of keeping broken farm equipment running, the ability to see past surface complexity to underlying principles, and the stubborn determination characteristic of people who've learned that impossible just means nobody's figured it out yet. The legacy persists in ways both visible and invisible. Kulin cutters appear in museums alongside the tanks they modified, physical artifacts of battlefield innovation that visitors can examine and photograph. Military doctrine includes formal procedures for evaluating soldier-developed modifications. Institutional recognition that some of the best ideas come from people actually using equipment under field conditions. Engineering schools teach the Kulin Cutter as a case study in problem solving, using it to illustrate how constraints often drive creativity and how simple solutions frequently outperform complex ones. And somewhere in the collective memory of the American military, the story survives as evidence that ordinary people doing extraordinary work can accomplish things that experts insist are impossible. The 12-cent breakthrough, measured by the scrap value of the steel rather than its ultimate worth, changed warfare by proving that innovation didn't require laboratories or extended development timelines or massive budgets. Sometimes it just required a farm boy from Tennessee who couldn't stop thinking about problems, a sergeant willing to test a crazy idea, a general willing to authorize mass production based on a single demonstration, and thousands of welders willing to work around the clock, turning scrap metal into life-saving equipment. This combination of individual insight and collective effort, repeated across countless applications, was perhaps the most important weapon America brought to World War II, more important than any specific technology, more decisive than numerical superiority, more enduring than any single victory. Curtis Culin died in 1963 at age 38 in an automobile accident in Tennessee, a quiet ending to a life that had intersected briefly with history before returning to normalcy. His obituary in the Knoxville newspaper mentioned his wartime service in a single paragraph and devoted more space to his community activities and survivors. Few of his neighbors knew the full story of what he'd accomplished during those 11 days in July 1944, when his modification helped break the Normandy stalemate. But in military archives, in historical records, in the memories of veterans who'd survived bocage fighting because tanks could suddenly crash through hedgerows in 28 seconds, Curtis Culin's legacy endured as proof that genius sometimes comes from unexpected places, and that the most important innovations often start with someone saying, "There has to be a better way." The hedgerows of Normandy still stand, ancient agricultural boundaries that nature and human labor created over centuries. The fields where Kulin cutters first proved their worth have returned to peaceful farming, and only small monuments indicate that history was made in these unremarkable places. But the principle Kulin demonstrated, that mechanical problems yield to mechanical solutions, that ingenuity matters more than credentials, that ordinary people can accomplish extraordinary things when necessity demands, that principle remains as valid today as it was in July 1944, when a farm boy from Tennessee looked at a piece of German steel and saw the solution to an impossible problem. The 12 cents worth of scrap metal saved 4,200 lives and changed the course of the war. That equation, that return on investment, stands as one of history's most dramatic examples of how small innovations can have enormous consequences when deployed at the right moment by people who refuse to accept that impossible means anything more than not yet achieved.